Hello friends. Recently I published an article on how to improve the convergence in the Madhava-Gregory Leibniz series. Now this series is used to calculate the value of pi, but they say it is not fit for practical applications. Now if you go on the internet, you go to Wikipedia and look at the Gregory series, which shows all the proof. At one point it talks that the convergence, right, because of its exceedingly slow convergence, it takes 5 billion terms to obtain 10 correct decimal digits. The Leibniz formula is not a very practical method for computing pi by 4. Finding ways to get around this slow convergence has been a subject of great mathematical interest. And because of this, people have used that formula and tinkered with it, put a lot of different numeric adjustments in it, and try to calculate the value of pi, or they have approached it from different methods. But you can still use this formula for calculating the value of pi. All you have to do is look at it in a different way. First we understand what it does. It basically calculates the length of this arc right here. This is the series, and this is its infinite series, with the variables. When t equals 1, the value becomes pi by 4. And all you have to do is multiply this value that you get by 4 and you get the value of pi. If you use trigonometry, you can actually come to this derivation right here. This is how I actually ended up looking up this problem. And when you come and arrive at this equation, the expansion is what you get as the arctan of t. So what I did was, when I was working on a mathematical system that I needed to create, I wanted a proof for it. So I was using trigonometry, and I came across some anomaly that actually was there in trigonometry, and I was having trouble. I thought the problem was with the way I calculated. But at that same time I noticed that there's a particular pattern to arctan. And I began to realize that if there was this pattern, that means there was a formula behind it. So I proceeded to derive the formula, and I used simple, in few steps, I was able to get the formula for pi. The only problem with this formula is this term right here has a pi in it, and having a pi to calculate pi doesn't make sense, right? So what I did was, I found out that if we convert this into a constant and find a way to calculate both these constants together, then I was able to actually get the value of pi. So that's what I did. I used an angle that I know of and took its cosine, used the cosine half angle formula, and repeated the process for a large number of iterations. Once I went to these large number of iterations, what I get over here is a cosine of a very tiny angle. Then I proceeded to get the tan of that tiny angle, even more so. I mean half angle tan of that angle. Then that means I have now got t, I have now got k. All I needed to do was plug it into the formula, and now with just few iterations I could calculate the value of pi up to, like, say 1000 digits, 2000 digits, 3000 digits. If I kept calculating a higher tan dip, what this formula is called, a tan dip. If I did a higher tan dip, I could even increase and calculate value of pi with very little terms, like just say 5 terms, 2 terms. At one point I thought, can I do it with just 1 term of the Madhava-Gregory Leibniz series? And that's where I stumbled upon this thing. All I needed to do was not even use the Madhava-Gregory Leibniz series, but just do a very high tan dip and just multiply k and t. And yes, you get the value of pi. It's amazing. That is related actually in trigonometry to this what we call identity, limit identity. So that is all there in the paper in the article that I published on the web. The link you can find in the notes below, and hopefully you will be able to take and understand and get more out of it. So thank you for watching my video, and all the best on your contributions to mathematics.